Hi guys, today we're going to learn about the vector equation of the line and the different forms of representing the vector equation of a line. So, the vector equation of a line in 2D is when a line in the xy plane is determined when a point on the line and the direction of the line, its slope or angle of inclination are given. That's what you learned back in Algebra 1 and middle school. Okay, so the equation of the line can be written in the point slope form as y minus y1 is equal to m times x minus x1. This is what you learned back in the day. Likewise, here in multi, we have that a line L in the two-dimensional space is determined when we know a point AB on L and a directional vector, let's call it UV. The vector equation of a line would be r of t is equal to the vector x comma y, and this is going to be equal to the vector u comma v, okay, times t plus the vector a comma b. Okay, so this is pretty much, okay, the equivalent of my point slope form but for multi. Okay, so if I ask you to find the vector equation of the line given that you have 2x minus 4y equals 12 and they tell you to use either an x-intercept or a y-intercept as your starting point, what are we going to do? To go back to your knowledge from Algebra 1, what we would do here is solve for y. So you have a point slope form. Okay, more than point slope, you would have a slope intercept form. Okay, so if I solve this equation, what would you have? Okay, so you would have something that looks like that. Y is going to be equal to 12. Okay, and it's going to be negative 12 because I passed the negative to the other side. Okay, so you would have negative 12. Okay, it would be plus, okay, 2x divided by 4. Okay, so you would have this equation, and this is going to be equal to positive 1/2 x minus 3. Okay, this gives you the equation y equals 1/2 x minus 3. This is nothing new. You have here the expectation, which it was a slope intercept form. Okay, so what we're going to do here is I'm going to let, okay, we're going to parameterize this equation. I'm going to let my t, the parameter, to be equal to x. Okay, so if I have that t is equal to x, then I know that y is going to be equal to 1/2 t instead of x minus 3. Do you agree with that? Because I'm parameterizing this equation. Given this, I have that r of t, okay, my vector equation of the line, it's equal to x comma y, okay, by the definition that we just have. Now you're going to tell me how in the world we're going to find u and v. Give me 1 second. Do you agree that when we were going over parametrics back in the day, you had that this is t and this is the y is going to be 1/2 t minus 3? So if we deconstruct this and we have the factors of t together as a vector, you would have something that is like this: 1 comma 1/2 t, y1 because 1 times t is t, okay, and then I would have plus and then the vector with the constants. In this case it would be 0, negative 3 because you don't have anything adding the t here, but you do have the minus 3 in the y component. Do you see it? Okay, therefore, okay, so you can say that r of t is going to be equal to the form that we have over here. If you want to go back to that one and be super extra, you can. Okay, so you have this equation, and that's your vector equation of the line. Okay, isn't that nice? Okay, so let's move on to more examples. We can also use vector equations to graph other structures. For example, this one, what you can see is this is your component x and this is your component y. So what you have here is that x is equal to t, but you know that y is equal to 1. So what's the business here? Well, you can see your best friend from also Algebra 1. So you can see that that situation that you have over there is an horizontal line. This is going to be your x. This is going to be your y. And if you have that, let's say that 1 is here, then the line that you have, the vt that we have is this one. This is going to be y equals 1. Isn't that nice? Another one that you can express here, you have that this is your x and this is your y. So you have that t, the parameter, is equal to y. Therefore, here you would have that x is equal to -2. So in a way, similarly to the previous one, but opposite, because this one is going to be a vertical line. Okay, so you can see that this is your y, this is your x, this is -2. Let's say that this is -2, so you can see that you are going to have a line over here, and that's going to be the expression that we have over here. Okay, so as the previous one, over here you have that v of t is equal to cosine t comma sine of t. So you have that your x is cosine and your y is sine of t. Okay, so this should give you vibes of pre-calculus. So you do know that cosine square of t plus sine square of t is equal to 1. Therefore, this should give you vibes of parametric equations where you know that x squared plus y squared is equal to 1. And here you can see that this is going to be your beautiful unit circle. Okay, so let me just write it over here, so you can see it very nicely, and you can recall your best friends in pre-calculus here, the unit circle and the trig identities. Okay, so let me just put it back there. So we can label this one. Okay, so you have that this is 1, this is 1, this is -1, this is -1. Now let's move on to this one. Technically speaking, what you have is x is equal to t and y is equal to t squared. So in other words, if x is equal to t and y is equal to t squared, then you have that y is equal to x squared. And what is this? Wow, that is the parent function of the quadratic equations, which you study a lot back in algebra 2. Okay, so you can see that we have that this one is the parent function y equals x squared. Okay, so now let's go to the next concept over here, the vector equation of a line in 3D. Okay, it's a line L in the three-dimensional space that is determined when we know a point, let's call it x0, y0, z0 on L. Okay, and the direction of L. Okay, the direction of the line in the space is any vector parallel to the line. Okay, so that's what we have. So if we let R to be the point x0, y0, z0 be any point, let's call it the position vector, okay, on the line L, and we let V, the vector ABC, be any vector parallel to the line L, we call this the direction vector of the line. The vector equation of the line that we covered on the previous page, you have that it's R of t is equal to R0 plus t times the vector b. In other words, you have that this apparent point is going to be a vector, okay, and then plus t times ABC. Okay, and this happens as the parameter t varies the above equation. Pretty much what it's going to do is going to trace out the line. Okay, so with this being said, this is the vector equation of the line. Okay, so the parametric equation of the line is going to be x is equal to x0 plus a times t. So pretty much what you are taking is you are taking the x component part of this vector equation of the line. Now for the y, similarly, you are going to take the y0, and remember that this t you distribute to this 3, so you have that it's going to be bt because of this one. Similarly, the z component, you have that it's going to be equal to z0 plus ct. Okay, so this is going to be what we call the parametric equation of the line. Similarly to this one, and this is equivalent to this. Now we have another one that it's the symmetric equation of the line. If we solve for t, this one, and this one, in each of the previous equations, and we write them as a triple equation, you are going to have that t is going to be equal, think about that, you move the x0 to the other side, pass the a dividing, so you have this. Similarly for this expression, you have that if you pass the y naught to the other side, it's going to be minus y naught, and then you're going to divide by v, and similarly here. So this, do you agree that all of them are equal to t? So what you can do here is you can equalize them. Okay, so you make them equal to each other because all of them are equal to t. So this is what we call the symmetric equation of the line, or the symmetric equations of the line. Please note that if one of the constants, let's say a, b, or c, because they are the denominator, they are 0, then you are going to omit that equation from the equality, and then, for example, let's say that a is equal to 0, then you are going to have that x is going to be equal to x naught, in which, in this case, the symmetric equations would be x equals x naught, which is a number, comma, and then the equality that we have over here with the y and the z component, they stay. Okay, so we're going to see examples like this in a second, so you can understand what is the business there. Okay, so let's move on to this example that we have in 3D. Okay, so given two 3D points, and you have P that it's 1, negative 2, 3, and Q that it's 1, 2, 5, they are asking you to find the following. First, the vector equation. To find the vector equation, you need a direction vector, which you don't have. You have a point. So from the vector P to Q, okay, you know that this is going to be equal to, let's call it the direction vector. And you know that from the beginning of class, this is going to be 1 minus 1, which is 0. Then you have 2 minus minus 2, which is going to be 4. And then you have 5 minus 3, which is going to be 2. So this is going to be, and I'm going to label here, your direction vector. Okay, or what we saw in the formula above as v. Okay, so with this being said, you have that the vector equation of the line is going to be r of t is equal to xyz. Okay, and this is going to be equal to what? It's going to be equal to something, okay, times t plus another vector. Okay, so you have pretty much this one and this one. Okay, so what is that? So for this equation, your direction vector is going to be the one that it's multiplying the t, and then the x naught, y naught, z naught is going to be one of the points that you have. In this case, I would use P, which you can make it a vector from the origin to here, which is 1, negative 2, 3. Okay, and this is what we call the vector equation of the line. Okay, so from this one, okay, once you have this one, the other two are very easy to get. Let me show you why. Okay, so you can notice that here, sadly, you can see that A is equal to 0. Okay, so you're going to tell me, oh, we have a situation like that. Yes. Okay, so you just need to be careful. Okay, so in this case, you have that X, okay, which is this one, is going to be equal to 1. Okay, so I'm going to leave that one alone. That's the example that we have over here. Then on the other side, okay, so this is the parametric equation, and you have that it's going to be 0 plus 1 x. Then you have your y. And parametric equations are these ones that we have over here. So you have that your y naught, okay, what's going to be your y naught here? Your y naught is going to be negative 2, okay, and you have that it's going to be plus 4t, okay. Why? Because I'm looking at the y components. Then I move on to my z, okay, my z component. What's the business? You have this and this, so you start with your z naught, which is 3, plus 2t. So that's what you have as the parametric equation. So now that we have the parametric equation, having the symmetric form of the line is simpler. You recognize that I don't have a t here, so that one I'm going to leave it like that. Then, okay, and this is the symmetric form, right? Or more over this one. I don't have the a, okay, here because a is 0, okay, so that's why I put it in this way. So now, following this idea, I have that this equation, okay, that equation that I have over there, is going to be what? It's going to be y plus 2, okay, divided by 4, okay, y, because I'm going to move the 2 to the other side, so it's a plus, and then divide by 4. On this one, what I'm going to do is going to be z minus 3 divided by 2, okay, so that's going to be your symmetric form. Now, here's a tricky question that I have for you. Does the line pass through the xz plane? You're going to tell me, why in the world is the x xz plane. Okay, so the xz plane is going to be where? Okay, where is the xz plane? Is when y is equal to 0. So ask yourself, is this something possible? So y equals 0 because that's the xz plane. So you equalize the y to 0, and that expression you equalize it to 0 and see if that makes sense. You pass the 2 to the other side, having 2 equals 4t. So you have that t is going to be equal to 1/2. So what's the conclusion here? You do have a situation, yes, okay, yes, the line, okay, passes, okay, through, okay, what was it? Through the xz plane, okay, at the point, okay, and this is happening at the point, okay. What's the point that we have here? We have that it's going to be the point, and you're going to plug this one here, here and here, so you have that it's going to be 1, okay, y1, because the x is always 1, then plug the 1/2 here. What happens there? You have that that's 0, and then you plug the 1/2 here, so making this a 1 plus 3, that's going to be 4, okay. So that's where the line, that's where the line passes through the xz plane, okay. So let's move on to see more examples on the next page. Now let's look at this example. They tell you that given the following linear equations, write the parametric equations, vector equations, and symmetric equations for each. Okay, so we have 2 examples here. Let's start with A. So in A you have that 2x is equal to y is equal to 4z. So what do you have here? So this, okay, it's a little bit wonky, okay. So you are like, how in the world they gave me that? So you are like, okay, so it means that this is equal to t, okay. So let's do this in parametric form first. What you are saying here is that 2x, and take this one with the t, is equal to t. Do you agree with that? Okay, so if that is true, I have that my x is going to be equal to t divided by 2. Do you agree with that? So now what's going to be your y? Your y is going to be equal to t, and what's the business for the z? The z is going to be equal to t divided by 4. Do you see it? Okay, so why? Because technically speaking you have that 2x is equal to t, y is equal to t, and 4z is equal to t, and then we are solving each other. Well, this is already solved here. Okay, do you see it? So this, okay, these 3 are the parametric form of that expression. Okay, so the next one that we have over here is when we have vector equations. That one, it means that it's r of t, or what we call xyz form. Okay, so you have that it's going to be some vector times t plus some other vector here. So we need the direction vector, okay. In addition to that, we need what? A point or something else. Here you already know, okay, that this is going to be a situation, or here more specifically, okay. So what do you have here? What you have is that the t, if we factor out the t here, you have a 1/2. If you factor out the t here, you have that it's 1, and if you factor out the t, you have that that's 1/4. Now ask yourself, do you have a constant here? No, so that constant in this component x is 0. Do you have a constant here? No, so the constant here is going to be 0. Do you have a constant here adding? Okay, no, so this is 0. So this is going to be your vector equation. You might tell me, how in the world that's 0, 0, 0? Because you don't have a constant here, okay, so here or here. Okay, so it's not always like that, but in this case it was like that. Now the symmetric equations. What are the symmetric equations? The symmetric equations are in the form x minus x naught divided by a. So what you have in this equation, what's going to be that? Your a, b, c, they are numbers. The ones that are problematic are the x naught, y naught, and z naught, and we didn't have any restriction for that. So what you have is x minus 0 divided by 1/2, okay, is equal to what? Y minus 0, okay, divided by 1, and z minus 0 divided by 1/4. Okay, so that is going to be the form of your symmetric equations. So you can see that, technically speaking, what we were seeing here at the beginning of the problem, it was in a form the symmetric equation of the line. Okay, so that's what you can conclude from there, but I just wanted you to see how it works. Okay, so yes, so let's move on to the last example of the day. Okay, so we have 2x plus 3z is equal to 12, and they tell you more information. Here what they are telling you is that it lies on the plane y equals 3. Okay, so how that can help you. Okay, so let's see. So what you know is, from this expression, you know that 3z is going to be equal to 12 minus 2x. Okay, so what you have is that z is going to be equal to 12 minus 2x divided by 3. Do you agree with that? Okay, in addition to that, we have that y is equal to 3 from the hypothesis of the problem. Okay, so technically speaking, okay, if we're talking about parameters, okay, we can parameterize this equation as follows. Parametric, you have that y is equal to 3, which is set. Okay, from here, then you can let x to be your parameter t. Okay, and then why I'm doing this, because I saw that x is an input of the z. Okay, so you have this, and then you have that z is going to be equal to 12 minus 2t divided by 3. Please note that this parameterization is not unique. Okay, if you parameterize differently, this is going to give you something different. Okay, so from here we can reduce this a little bit if you want, or you can leave it like that as 4, because 12 divided by 3 is 4 minus 2/3 t. Are we okay with that? So this could be your 3 parametric equations, and that would be beautiful. Okay, following the parametric equations that we have, the vector equation r of t is equal to, remember, x, y, z. Okay, and then you're going to have that it's going to be something times t plus another vector here. Okay, so what do you have here? Well, you can see, okay, very nicely, okay, the factors that we have here. Okay, so the factors of t, you can see that here, what do you have? That's 1. Okay, the factor on the y, what do you have? Do you have a t value here? No, so that one is going to be 0 because we don't have t's. Then for z, you have that the factor is going to be negative 2/3. Okay, so that's what we have for this situation. Now, what are we going to have here? Well, you're going to have the constants of each. Start always with the x. Even though I put the y first, it doesn't matter. You always start x, y, z. So here you have that there's no constant. Okay, so that's 0. Then you can see that this one is going to be 3, and this one is going to be what? 4. So this is going to be your vector equation of the line. Okay, now let's move on to the symmetric equations of the line. Now, the one that is going to be problematic in this specific example is the y, because y is going to be equal to 3, so that one is going to live there alone because it doesn't have t. Okay, now what you have is, you have that the x is going to be x divided by 1, because you know that the x naught, what's the x naught? 0. Do you see it? So it's x minus 0 divided by 1, and then the y, we already talked about the y, and then last but not least, we have that the z is going to be z minus 4, okay, yes, divided by, because your x, your z naught is 4, and then divided by negative 2/3. Whether you simplify this or not, it's up to you, but I'm leaving it like that so you understand how it works exactly as a formula. Okay, so I hope that you find this video helpful, and remember, if you have any questions, write them in the comments, and bye.